Hello everyone, a very good evening to all. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So I welcome you all once again for this introduction session on solid state physics. This is our ninth introduction session. So the solid state physics course is being taught this semester by NPTEL in July 2024 session with course code NOC 24 PH43. So today we will solve a few problems that will be covering the week 8 and week 9 lectures of the course. So let's start with solving the problems related to the course content. Question number 1, it says estimate the temperature at which diamond will have the same conductivity as silicon at room temperature, that is 300 Kelvin. The band gap of silicon is 1.1 electron volt and for diamond is 5.4 electron volt. Consider the conductivity of intrinsic semiconductor. Obey the following relation, that is sigma equals to K exponential minus Eg by 2 kBt, where K is the Boltzmann constant and E is the band gap. The value of the Boltzmann constant is also given. Kb is equals to 1.38 into 10 to the power minus 23 joule per Kelvin. And the options are option A 1472 Kelvin, option B 1562 Kelvin, option C 1672 Kelvin, and option D 1792 Kelvin. So we need to estimate the temperature at which both diamond and silicon will be having same conductivity. So uh, the conductivity of silicon at room temperature. So the conductivity that silicon has at room temperature, if diamond has to match that conductivity, then what should be the temperature so that the conductivity of diamond will be same as that of the conductivity of silicon at room temperature. So this is the formula that we will use. The formula is sigma equals to K exponential minus Eg by 2 kBt, where K is the Boltzmann's constant that is given 1.38 into 10 to the power minus 23 joule per Kelvin, and Eg is the band gap energy, which is Eg for diamond is 5.4 eV and Eg for silicon is 1.1 eV. So we will put these values in the formula and we will equate the two values and we can easily calculate the temperature because the temperature is present in the denominator here. So we can calculate the temperature at which diamond will be having same conductivity as that of silicon at room temperature. So I'll give you a few minutes to solve this and then I will discuss what will be the correct option for this question. So if we solve it, then sigma for silicon will be K exponential minus Eg. Eg is 1.1 for silicon, and it is 2 Kb into T, and T is 300 for silicon, and for diamond is K exponential minus 5.4 is the band gap energy for diamond, then 2 Kb into T. So if we equate these two, then we will get K exponential minus 1.1 by 600 kb equals to K exponential minus 5.4 by 2 kbt. So very simply we can say 1.1 by 600 kb is equals to 5.4 by 2 kbt. So again kb gets cancelled out, and if it 2 cancel, it will be 300. So T will be 5.4 into 300 divided by 1.1. So T will be 1472 Kelvin. So at 1472 Kelvin, the conductivity of diamond will be equal to that of the conductivity of silicon at room temperature. Now you can see here the conductivity increases with temperature, because if you see the relation of the conductivity, it is sigma equals to K exponential minus Eg by 2 kBt. So since the T is at the denominator, and again the exponential factor is negative, so if T increases, the conductivity will increase. So com in order to make the two conductivities equal, now you see it also depends upon the band gap. So with increase in band gap, the conductivity decreases. So the conductivity diamond has at room temperature is less as compared to the silicon, because the silicon has the band gap energy of 1.1 electron volt, but diamond has 5.4 electron volt, which is roughly 5 times. So the conductivity will be less than the conductivity of diamond will be less than that of silicon by up to exponential e to the power 5 times. So in order to increase the conductivity to the conductivity that will be equal to the conductivity of silicon at room temperature, we need to increase the temperature, because only then the electrons from the conduction band will be from the valence band will be able to come to the conduction band by overcoming the band gap, which is quite high, that is 5.4 electron volt. So you see the conductivity will be equal to the room temperature conductivity of silicon at 1472 Kelvin, or we can say it is around, if you 273, it is around 1199 degrees Celsius. So at this temperature, the conductivity of diamond will be equal to the conductivity of silicon at T equal to 300 Kelvin. I hope this is clear to everyone. Now we will move to the next question. The question says, find out the fraction of electrons excited into the conduction band in germanium at 100 K if the band gap of germanium is 0.7 electron volt. The Boltzmann constant is again given 5.38 into 10 to the power minus 23 joule per Kelvin. The options are option A 1.13 into 10 to the power minus 15, 2.38 into 10 to the power minus 18, 4.32 into 10 to the power minus 21. Option D, 5.12 into 10 to the power minus 23. So the question says, find out the fraction of electrons that are excited into the conduction band in germanium at 100K. So we will use a formula. You must have read about that expression in your week's lecture. So you will use there is a particular relation that relates the intensity to that of the temperature and band gap. So we will use that formula and we will calculate the fraction of electron that will be excited into the conduction band. Because I told you uh, why they are called as semiconductor, because the energy difference between the valence band and conduction band, which is also known as the band gap, is there is some minimum band gap, that is 0.7 electron volt in this case. So in order to conduct electricity, the electrons need to go to conduction band from valence band. So they need some energy. So here, since the temperature is 100K, so due to this 100K temperature, this temperature is equivalent to some amount of energy, and due to that energy, some electron from conduction band will definitely be excited to the some electron from the valence band will definitely be excited to the conduction band. So here we will calculate that density only. So I'll give you a few minutes to try this question, and then I will discuss how we will solve this question. So there is a relation for calculating the concentration of electrons in conduction band in case of a semiconductor. So the relation can be derived by using distribution function of electron and the concept of density of states. And in the previous introduction session also we had discussed the distribution function of electrons, that is the Fermi distribution given by SNE, which also indicates the probability of occupation is 1 by 1 plus exponential E minus EF by kBT, where EF is the Fermi energy. So if we use this relation, and we can derive the expression for concentration of electrons in the conduction band, and the relation is like, then the relation has the form N equals to NC exponential minus EC minus EF by kBT. So here NC is a constant, which is also called as, where N is the concentration of electrons in the conduction band, NC is the constant, which is the effective density of states in the conduction band. That is the effective density of states in the conduction band, which can, so the expression for NC is 2 pi m kBT by h square to the power 3 by 2. This is the effective density of states in the conduction band, or we can call it as the total number of electrons available for excitation from the valence band. So this is also called as total number of available electrons for excitation from the top of valence band. So you see, this is the total number of electrons that are available for excitation, and this is the number of electrons that is present in the conduction band. So in the question, it has mentioned us to find out the fraction of electrons excited into the conduction band. So the fraction of electron excited into the conduction band, the fraction of electrons excited into the conduction band will be small n by nc. So this is equals to exponential minus EC minus EF by kBT minus EC minus EF by kBT. And we know for intrinsic semiconductors, EC minus EF is equals to EG by 2. So N by NC will be equals to exponential minus EG by 2 kBT, which is exponential minus 0.7 into 1.6 into 10 to the power minus 19 divided by 2 into 1.38 into 10 to the power minus 23 into 100, because T is 100 Kelvin given in the question. Kb we know, and the band gap Eg is given as 0.7 EB. So if you convert it to electron volt, we will multiply 0.7 into 1.6 into 10 to the power minus 19 from electron volt to joule. Because here we are putting Kelvin and joule per Kelvin, so the denominator is also in the form of joule. So we need to convert the energy from electron volt into joule so that the exponential term will be dimensionless. So if you calculate it, it will be 2.38 into 10 to the power minus 18. So you see, this is the fraction, that is, if there are some amount of electron present, only 2.38 into 10 to the power minus 18 fraction of electrons will be excited from uh, the valence band to the conduction band. So the conductivity of uh, semiconductors lies that of between the conductivity of conductors and insulators, because they have some energy, there are some band gap between conduction band and valence band, and the fraction of electrons excited from the valence band into the conduction band is very less. So this is the correct answer, and the correct option will be option B, that is 2.38 into 10 to the power minus 18. I hope this is clear to everyone. Now we'll move to the next question. The question number 3 says the resistivity of an intrinsic germanium at 27 degrees Celsius is 0.43 ohm meter. Calculate the intrinsic carrier density at 27 degrees Celsius and consider the mobility of electrons and holes in germanium are 0.39 meter square per volt into second and 0.19 meter square per volt into second respectively. So the resistivity of intrinsic semiconductor is given. Also the mobility of the electrons are given. We need to find out the intrinsic carrier density. The options are option A 2.1 into 10 to the power 15 per meter cube. Option B 4.1 into 10 to the power 17 per meter cube. 2.5 into 10 to the power 19 per meter cube. And option D 6.7 into 10 to the power 25 per meter cube. So I'll give a few minutes to try this question, and then I will discuss how we will solve this question. So we know the expression for conductivity is Ne mu E plus Pe mu P. And for intrinsic semiconductors, both N equals to P equals to Ni, that is the intrinsic carrier density. So it will be Ni E mu E plus P mu P. Here we need to find out the intrinsic carrier density. So the intrinsic carrier density Ni will be conductivity sigma by E mu E plus P mu P. And we know sigma is equals to 1 by rho, where rho is resistivity. So Ni equals to 1 by rho E mu E plus mu P, where the charge of electron and hole both are same. So it is 1.6 into 10 to the minus 19 coulomb. So we can take it as the value of E also. So it will be 1 by the resistivity is given, it is 0.43 ohm into meter into 1.6 into 10 to the power minus 19. Then the mobility of electron and hole is also given. The mobility of electron is 0.39 and the mobility of hole is 0.19. So if you calculate it, it will give you 2.5 into 10 to the power 19 per meter cube. So the intrinsic carrier concentration for germanium at room temperature having a resistivity of 0.43 ohm into meter is 2.5 into 10 to the power 19 per meter cube. So the correct option is option C, 2.5 into 10 to the power 19 per meter cube. Now moving to question number 4. The question says the intrinsic carrier density of germanium at room temperature, that is T equal to 300 Kelvin, is 2.5 into 10 to the power 19 per meter cube. Assuming that the number of electrons near the top of the valence band available for the thermal excitation at T equals to 300 Kelvin is 5 into 10 to the power 25 per meter cube. Calculate the band gap energy for germanium, where the Boltzmann's constant is 1.38 into 10 to the power minus 23 joule per Kelvin. The options are 1.1 electron volt, 0.25 electron volt, 0.75 electron volt, and D 5.4 electron volt. So the question is pretty much similar to the previous question that we had solved. So the question was calculate the fraction of electrons excited into the conduction band, and the band gap was given and the temperature was given. But here the intrinsic carrier density is given, the number of electrons available in the thermal excitation, available in the valence band for thermal excitation, that value is also given. We need to find out the band gap energy of germanium. So we will use that same expression, but here the unknown is band gap energy, that is Eg, and N is the intrinsic carrier density, intrinsic charge carrier density, and the constant Nc is the total number of electrons available for thermal excitation. Total number of electrons available in the valence band for thermal excitation. So we'll use the same formula n equals to nc exponential minus Eg by 2 kBt, and we'll calculate the band gap energy. So I'll give you a few minutes to try this question, and then I will discuss how we will calculate the band gap energy for germanium at the temperature, room temperature. So if we calculate, we have Kb is 1.38 into 10 to the power minus 23 joule per Kelvin. T is 300 Kelvin. Ni is 2.5 into 10 to the power 19. N is 5 into 10 to the power 25. So Ni by N is equals to exponential minus Eg by 2 kBt. Then if you take ln on both sides, ln N by Ni will be Eg by 2 kBt. Since here it was minus, this minus, with this minus, the N by N, Ni by N gets converted into N by Ni. So Eg will be 2 kBt ln n by ni. So Eg will be 2 into 1.38 into 10 to the power minus 23 into 300 into ln 5 into 10 to the power 25 divided by 2.5 into 10 to the power 19. It will be 1.2 into 10 to the power minus 19 joule. So if you convert it into electron volt, it will be 0.75 electron volt. So this is the answer, and you see the options. The correct option is option C. So here the band gap energy. So the band gap energy for germanium is 0.75, which is the obvious thing because we know the band gap energy for germanium is 0.7 electron volt. So, but one more thing, if you notice here, you can see here the temperature is 300 Kelvin, and from the questions, the intrinsic charge carrier density is 10 to the power 9 in terms of in the order of 10 to the power 19 per meter cube, and the total number of electrons available is 10 to the power 25 per meter cube. So the fraction of electrons from the fraction of electrons that up in the conduction band to the number of electrons available for excitation is around 10 to the power minus 6. But in the previous question we calculated the fraction of 10 to the power minus 18. Why it was so less in the earlier case? Because the temperature was only 100 Kelvin. So you see, as you go below the room temperature, the fraction of electrons that are available, that the fraction of electrons that were available in the valence band but were able to excite into the conduction bands for conduction of electricity reduces significantly. So at room temperature, the ratio is only 10 to the power minus 6, but at 100 Kelvin, that is around minus 150, roughly 170 degrees Celsius, the ratio is quite low, that is 10 to the power minus 18 in comparison to the total number of electrons available. Now we'll move to the next question. The question says, indium phosphide has an energy gap of 1.29 electron volt. The electron and hole mobilities for this semiconducting compound are 0.46 and 0.015 meter square per volt into second respectively at 300 Kelvin. Calculate its conductivity at 300 Kelvin. Consider that at 300 Kelvin, the effective density of states in conduction band is 4.4 into 10 to the power 25 per meter cube. The Boltzmann constant value is also given. The options are option A 5 into 10 to the power 5, option B 7 into 10 to the power minus 5, option C 9 into 10 to the power minus 5, or option D 11 10 to the power minus 5 ohm inverse meter inverse. Because here we need to find out the conductivity. So the unit of conductivity is reciprocal of that of the resistivity, and the unit of resistivity is ohm into meter. So here it is given as indium phosphide. So indium phosphide has an energy gap of 1.29 electron volt. So the energy gap is given 1.29 electron volt. The electron and hole mobilities for this semiconductor compound is given. So the electron mobility mu e is 0.46. The hole mobility mu p is 0.015. All these are at temperature of 300 Kelvin, and we need to find out the conductivity at 300 Kelvin. And what we have to put? The effective density of states in conduction band, that is NC, is equals to 4.4 into 10 to the power 25 for meter cube. So I'll give a few minutes to try this question and then I will discuss what will be the correct option. So here we need to find out the conductivity, and we know for an intrinsic semiconductor, the conductivity is given by Ni E mu E plus P mu P, or Nie mu E plus mu P here. But if you see the question, here we don't know the value of Ni, that is the intrinsic carrier concentration. So here we will put the expression that we have been using in the previous questions, that is E mu E plus mu P into, in place of intrinsic carrier concentration, it will be Nc exponential minus Eg by 2 kBt, where we know Nc is the effective density of states in the conduction band. So if you put those values, 1.6 into 10 to the power minus 19, then 0.46 plus 0.015 into Nc is also given 4.4 into 10 to the power 25, then exponential. The band gap is again given, it is 1.29 electron volt. So 1.29 into 1.6 10 to the power minus 19 divided by 2 kBt, 2 into 1.38 into 10 to the power minus 23 into the temperature is 300. So if you calculate, it will come around 4.99 into 10 to the power minus 5 ohm meter, or 5 into 10 to the power 5 ohm inverse meter inverse. So this is the correct answer, and if you see the options, the correct option is option A. So I hope this is clear to everyone. We wrote the expression for conductivity, and in place of intrinsic carrier concentration, we use the formula. That is the expression which relates the intrinsic carrier concentration with band gap, temperature, and the effective density of states in the conduction band. That is the constant Nc. Now we will move to the question number 6. The question says, consider Nd equals to Nc exponential Ec minus Ed by kBt, where N D is the density of electrons occupying in the donor level, Nc is the effective number of density of states of electron in the conduction band, and Ec minus Ed is called the ionization energy of the donors. That is the energy difference between the donor level and the conduction band. Now calculate the fraction of donor electrons prompted to the conduction band, that is Nd by Nc, at 27 degrees Celsius, that is again at room temperature, that is 300 Kelvin also. For the donor ionization energy in germanium doped with phosphorus, the ionization energy is 0.012 eV. So in the question what we have, the expression for donor density Nd is given by Nc exponential minus Ec minus Ed by kBt, where Nd is the density of electrons in the donor level, Nc we know it is the effective density of states in the conduction band. Ec minus Ed It is the ionization energy, and this ionization energy is given as 0.012 ev. That is the ionization energy in germanium doped with phosphorus. So phosphorus, we know phosphorus has valency of 5, so it can give an additional electron. It has an additional electron in the valence band, so it gives the additional electron to the donor level. So it is an extrinsic semiconductor, and the impurities, and also basically it is an n-type semiconductor with donor impurities. And we need to find out the fraction of donor electrons promoted to the conduction band, that is Nd by Nc. So I'll give a few minutes to solve this, and then I will tell you what will be the correct option. So if we solve it simply, we need to put the expression Nd by Nc equals to exponential minus EC minus ED by KBT. It will be exponential minus 0.012 into 1.6 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 300. So if you calculate, it will be 0.628, approximately 0.63. So the correct option will be option B, that is 0.63. Now we move to the question number 7. The question says, consider Na equals to Nb exponential minus Ea minus Eb by kBt, where Na is the density of holes occupying the acceptor level, Nb is the effective number of density of states in the valence band. Calculate the fraction of holes present at 300 Kelvin in silicon doped with indium. The acceptor level is 0.16 electron volt above the top of the valence band energy level. So this question is exactly similar to the previous question, but here we are considering the case of a p-type semiconductor because there are acceptor atoms and acceptor level here, and the difference between the acceptor level and the valence band level is 0.16 electron volt. So again, we will use the same formula and we will calculate the same quantity, that is Na by Nb, but for another type of semiconductor here, p-type semiconductor, because they have acceptor atoms or acceptor impurities. So I'll give a few minutes to try this question and then I will discuss what will be the correct option. So if we calculate similarly to the previous question, it will be NA by NB to exponential minus EA minus EB by ABT exponential minus 0.16 into 1.6 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 300. So if you calculate, it will give you 2 into 10 to the power minus 3. The correct option will be option B. So this question was pretty much similar to the previous one. So we don't need to discuss it further. So we will move to the next question. Question number 8 says a rod of P-type germanium 10 mm long and 1 mm in diameter has a resistance of 100 ohm. What is the concentration of the impurity in this rod? Consider the conductivity in germanium is only due to holes for impurity atoms. The mobility of holes in germanium is given by mu h, which is 0.13 meter square for volt into second. Options are option A 3.24 into 10 to the power 25, option B 2.10 into 10 to the power 13, option C is 6.12 into 10 to the power 21, and option D 4.47 into 10 to the power 28. So here there is a rod of P-type germanium, P-type germanium rod. Length is 10 mm, diameter is 1 mm, and it has resistance 100 ohm, and the mobility of holes is 0.13 meter square volt into second. So what is the conductivity? Sorry, what is the concentration of impurity? So I'll give you a few minutes to try this question, and then we will discuss how we will solve this question. So if we solve it, we know the expression for conductivity. We know conductivity is given by Ne mu e plus Np mu p. So here in the question it says consider the conductivity of germanium is only due to holes of impurity atoms. So we will neglect this, and the constant and the conductivity will be mainly due to the density of the donor atom. That is the density of donor atoms. We will replace N with Nd, then charge E, and then the mobility of the donor atoms mu d. So this is the expression NdE mu d. Now, but how we will calculate? So we need to find out Nd, which is activity by E mu d. But we don't know the value of conductivity. So from the information given in the question, length of the germanium rod is 10 mm, resistance is given to us, and diameter is also 1 mm, that is given to us. So from all those informations, we can calculate the resistivity, because we know the resistivity rho equals to R A by L, where A is the area cross section, L is the length, and R is the resistance. And then the conductivity will be 1 by rho, that is L by RA. So what will be the value of Na? Na is 1 by rho E mu d, because here it was sigma by E mu d. So in place of sigma, we will put 1 by rho. So it will be 1 by rho E mu d. So and again, rho is Ra by L, where R is 100 ohm, we know. A will be pi r square, which is 3.14 into 10 to the power minus 3 by 2. 1 mm is the diameter. So converting into meter, it will be 10 to the minus 3, and the radius will be by 2. So it will be square. Then L is 10 mm is given to us. So it will be 10 to the power minus 3 meter square. So if we put those values, Na will be 1 by. So first we need to find out the resistivity. So the resistivity rho will be Ra by L. It is 100 into 3.14 into 10 to the power minus 3 by 2 square divided by L is 10 into 10 to the power minus 3 meter, so which will come around 7.85 into 10 to the power minus 3 ohm into meter. So the donor atom density will be 1 by rho E mu d, that is 1 by 7.85 into 10 to the power minus 3 into 1.6 into 10 to the power minus 19 into mu d is 0.13. So if you calculate it, it will give you 6.12 into 10 to the power 21 per meter cube. This is the correct answer. 6.12 into 10 to the power 21 per meter cube. That is option C is the correct option. Now move to the ninth question. The question says calculate the drift velocity of an electron moving in a germanium crystal in an electric field of 10 to the power 3 volt per meter. The mobility of electron in germanium is mu e is equal to 0.39 meter square per volt into second. This is a pretty straightforward question. We know the relationship between the so there is expression that relates mobility, velocity, drift velocity, and electricity. So if you put that relation, the two values are known. The only unknown is the drift velocity of the electron, and you can calculate very easily. So I'll give you 1 or 2 minutes to calculate it, and then I will discuss whether your option is correct or not. So if you calculate it, so there is expression mu is equals to Vd by E, where Vd is the drift velocity. So Vd is equals to, sorry, Vd equals to mu into E. So it will be 0.39 into 10 to the power 3, that is 390 meter per second. It is option B. So question number 10, the question says 5 gram of N-type silicon doped with arsenic, conductivity 10 to the conductivity 10 ohm inverse meter inverse is melted with 5 gram of P-type silicon doped with aluminum having the same conductivity. What is the conductivity of the resulting material? The mobility of the electrons in silicon is 0.14 and for hole is 0.05 meter square per volt into second. Consider complete ionization and conductivity in the resulting material is due to only average charge carriers of holes. So let's read the question once again. 5 gram of N-type silicon is doped with arsenic of conductivity 10 ohm inverse meter inverse and it is melted with 5 gram of P-type silicon that is doped with aluminum and both are same conductivity. So what will be the conductivity of conductivity of the resulting material, and we have to take the mobility of electrons in silicon is 0.14 meter square per volt into second and for hole is 0.05, and we have to consider complete ionization and the conductivity in the resulting material is due to only average charge carrier of holes. The options are option A 9.3 ohm inverse meter inverse, option B 6.4 ohm inverse meter inverse, option C 3.2 and option D 1.6. So this is very good question. So I'll give you a few minutes to think about it and try, and then I will discuss how we will approach this question and how we will solve it. So here You see the conductivity of, so here it is given 5 gram of n-type silicon, which is doped with arsenic, has the conductivity of 10, and again 5 gram of p-type silicon doped with aluminum. So both have same conductivity. Now, if we want to find out what will be the charge carrier result in the resulting material, so we need to find out the nature of the resulting material that will be formed by melting these two types, n-type of n-type silicon and p-type silicon. Since both are being melted and being mixed together to produce a new material. So, so you see, we know the expression for conductivity is Ne mu e plus Np, sorry, Pe mu p. But for extrinsic semiconductors, for p type, this will be Na E mu a, and for n type it will be Nd E mu d, where Nd is the donor density, Na is the, so Nd is the donor density and mu d is the donor mobility. Similarly, Na is the acceptor density and mu a is the acceptor mobility. Now, if you calculate the densities, so Nd will be sigma by E mu e. So here you see both are, the mass is same, 5 gram, 5 gram, 5 gram, but since they have different mobility and the concentration depends upon the conductivity and mobility. So depending upon the value of the mobility, their concentration will be different. So the concentration of donor, that is the donor density, will be sigma by E mu e, which will be 10 by 1.6 into 10 to the power minus 19 into 0.14, which is 4.46 into 10 to the power 20 per meter cube. Now similarly, the density of the acceptors will be Na sigma by E mu h will be 10 by 1.6 into 10 to the power minus 19 into 0.05, which is 1.25 into 10 to the power 21 per meter cube. So now you see the density of acceptor is greater than the density of donor. So the resulting material should be p type. Now, if we talk about the density of the resulting material, sorry, the conductivity of the resulting material, then in the question it is mentioned that consider the complete ionization and the conductivity in the resulting material is due to only average charge carrier of holes. So the average charge carrier of holes will be, so the conductivity, if we consider, will be E mu d, because, sorry, not mu d, it is H, because of holes it is H, and the average hole concentration will be Na minus Nd by 2. So sigma will be 1.6 into 10 to the power minus 19 into 0.05 into 1.25 into 10 to the power 21 minus 4.4 into 10 to the power 20 divided by 2. So it will be, if you calculate, it will come out 3.2 ohm inverse meter inverse. So the conductivity of the resultant material will be 3.2 ohm inverse meter inverse. So we'll move to the next question, which is the last question of today's introduction session. The question says, determine the intrinsic concentration of charge carriers in a pure sample of silicon at room temperature, that is 300 Kelvin. The effective mass of electron is 0.7 mass. So effective mass is, we know, when an electron or hole travel, when an electron travel inside the crystal, the mass is termed as effective mass, and which is not equal to the actual mass of electron. So here the effective mass of electron is Me star, which is 0.7 times the actual mass of electron, and that of the hole is equal to the mass of electron, where we know the mass of electron is 9.1 into 10 to the power minus 31 kg. The band gap energy is given, which is 1 electron volt. The Boltzmann constant Kb equals to 1.38 into 10 to the power minus 23 joule per Kelvin, and the Planck's constant is 6.6 into 10 to the power minus 34 joule into second. The options are option A 7.73 into 10 to the power 16 per meter cube, option B 9.23 into 10 to the power 21 per meter cube, option C 6.23 into 10 to the power 28 per meter cube, and option D 1.45 into 10 to the power 41 per meter cube. So we need to find out the intrinsic concentration of charge carriers of a pure sample of silicon at room temperature, where the effective mass is given, the effective mass of electron and the effective mass of hole is given, and the band gap energy is given. So we will use a formula that you have gone through in the, you definitely have come across during the lectures of this course. So we'll use that formula for calculating the intrinsic charge carriers. And if you put those values in that formula, we can easily calculate the value of intrinsic charge carriers. So I'll give you a few minutes to try this question, and then I will discuss how I will how we will solve this question. So if you know the expression, it's intrinsic charge carriers. Ni will be equals to 2 pi kbt, sorry, so this is the expression for intrinsic charge carrier, where Me star is the effective mass of electron, that is 0.7 m, and Mh star is the effective mass of hole, that is m, where Me is the mass of electron, that is 9.10 - 31 kg, and the energy band gap is 1 electron volt. So if you put those values, it will be 2 into 3.14 into 10 to the power into minus 23 into 1.38 into 300 room temperature T. Then H square 6.6 into 10 to the power minus 34 square to the power 3 by 2. So it will be 0.7 into 1 into the mass of electron, that is 9.1 10 to the power minus 31 kg whole square to the power 3 by 4 exponential minus 1 into 1.6 into 10 to the power minus 19 divided by 2 into kBt, 1.38 into 10 to the power minus 23 into 300. So it will come out 2.91 into 10 to the power 70 into 6.64 into 10 to the power minus 46 into 4 into 10 to the power minus 9. It will be 7.73 into 10 to the power 16 per meter cube. So the correct option is 7.73 into 10 to the power 16 per meter cube. So the correct option is option A. So I hope this all the questions were clear to you, and it will definitely help you in solving your assignment problems. And also, if you are registering for the exams at the end of the semester, it will definitely help you in your exams also. With this, I stop today's interaction session. I thank you all for being a part of this course. That's it for my side for today.